Namaste, dear learners. We are aware that a current carrying conductor has a magnetic field associated with it. We've already performed experiments to understand the same. At the end of today's session, we'll be able to differentiate between three scenarios: magnetic field by a straight current carrying conductor, magnetic field by a circular current carrying conductor, and magnetic field produced by a solenoid. Can we also draw a conclusion that a current carrying wire placed in a magnetic field behave in a particular way? Let's find out. A convenient way of finding the direction of magnetic field associated with a current carrying conductor is the right hand thumb rule, which states, imagine you are holding a current carrying straight conductor in your right hand like this, such that the thumb points in the direction of the current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. This is known as the right hand thumb rule. Assume that the current is flowing through a horizontal power line, flows in east to west direction like this. What is the direction of magnetic field at a point directly below it and at a point directly above it? Now, applying the right hand thumb rule, we get that the direction of magnetic field at a point below. So, imagine I have a wire placed in my hand. Now, applying the right hand thumb rule, we get that the direction of magnetic field at a point below the wire is from north to south, and the direction of the magnetic field at a point directly above the wire is from south to north, like this. We have so far observed the pattern of magnetic field lines produced around a current carrying straight wire. Suppose the straight wire is bent in the form of a circular loop and a current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Similarly, at every point of the current carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. By the time we reach the center of the circular loop, the arcs of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to magnetic field appearing as straight lines at the center of the loop. So by applying the right hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. This rule is also called Maxwell's corkscrew rule. If we consider ourselves driving a corkscrew in the direction of the current, then the direction of the corkscrew is the direction of the magnetic field. We know that the magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Therefore, if a circular coil has n turns, then the field produced is n times as large as produced by a single turn of wire. This is because the current in each circular turn has same direction, and the field due to each turn then just adds up. A coil of many circular turns of insulated copper wire wrapped closely in the shape of the cylinder is called a solenoid. Now let's get a pattern of magnetic field lines around a current carrying solenoid. As you can see on your screen, if we compare this pattern of the field with the magnetic field around a bar magnet, do you see some similarity? Absolutely yes. They are exactly similar to each other. In fact, one end of the solenoid behaves like a magnetic north pole, while the other behaves like a south pole. The field lines inside a solenoid are in the form of parallel straight lines. This indicates that magnetic field is the same as at all points inside the solenoid. That is, the field is uniform inside the solenoid. Now, a strong magnetic field is produced inside a solenoid, and it can actually use to magnetize a piece of any magnetic material like a soft iron. In this case, I have used an iron nail and a copper wire has been wound around it. The magnet which is so formed is called an electromagnet. This iron nail will be behaving like a magnet when it is connected to two terminals of a battery. Now, the French scientist André-Marie Ampère suggested that a current-carrying conductor placed in a magnetic field experiences a force. The force due to a magnetic field acting on a current-carrying conductor can be demonstrated by an activity. For that, you just need to take a small aluminium rod, maybe of 5 centimeters length. Using the connecting wires, you can suspend it horizontally from a stand. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. For this, you put the north pole of the magnet below and south pole of the magnet vertically above the aluminium rod. Connect the aluminium rod in series with a battery, a key and a rheostat, and now pass the current through the aluminium rod from end B to end A. It is observed that the rod is displaced towards the left. Reverse the direction of current flowing through the rod and observe the direction of displacement. It now moves towards the right. Why does the rod get displaced? The displacement of the rod in the above discussed activity just suggests that the force is exerted on a current carrying aluminium rod when it is placed in an external magnetic field. It also suggests that the direction of force is reversed when the direction of current through the conductor is reversed. Now change the direction of field to vertically downwards by interchanging the two poles of the magnet. It will be observed by you that the direction of force acting on the current carrying rod gets reversed. This shows that the direction of the force on the conductor depends on the direction of current and the direction of magnetic field. Experiments have shown that displacement of the rod is the largest when the direction of current is at right angles to the direction of the magnetic field. In such a condition, we use a simple rule to find out the direction of force on the conductor. We considered the direction of the current and that of the magnetic field perpendicular and found that the force is perpendicular to both of them. The three directions can be illustrated through a simple rule called Fleming's left hand rule. According to this rule, if you stretch your thumb, forefinger, middle finger of your left hand in such a way that they are mutually perpendicular to each other, then the first finger points in the direction of magnetic field. The second finger will point in the direction of current, and thumb will point in the direction of motion or the force along acting on the conductor. This can be used to demonstrate a device called an electric motor. Children, remember that electric motor is a device which converts electrical energy into mechanical energy. It is used as an important component in an electric fan, refrigerators, mixers, washing machine, computers, MP3 players, etc. An electric motor consists of a rectangular coil ABCD of insulated copper wire. The coil is placed between two poles of a magnetic field such that the arm AB and CD are perpendicular to the direction of magnetic field. The ends of the coil are connected to the two halves P and Q of a split ring. The inner sides of these halves are insulated and are attached to an axle. The external conducting edges of P and Q touch two stationary brushes, X and Y, which are conducting in nature. Now, current in the coil ABCD enters from the source battery through the conducting brush X and flows back into the battery through brush Y. Notice that the current in the arm AB of the coil flows from A to B, and in arm CD it flows from C to D. I am going to show how exactly the coil moves, and we will also learn how to apply the Fleming's left hand rule in this situation. You have to imagine that this is a coil ABCD and it is placed between two poles of the magnet. Imagine, north pole of the magnet is on this side and south pole is on this side. We all know that magnetic lines of forces are always from north to south. So, just for representational purpose, I have got this arrow which will give you an idea of the direction of magnetic field. Now, look at this carefully. The coil A, B, C, D. The current is flowing from A to B and from C to D, and the external magnetic field, the direction is clear to you. Now, if I apply Fleming's left hand rule, I will find out in which direction will the coil move. Let us apply Fleming's left hand rule in the arm CD of the coil. So, what does the rule state? If I stretch the thumb, the first finger and the second finger of my left hand mutually perpendicular to each other, then my first finger should give the direction of magnetic field. So, here my forefinger is giving the direction of magnetic field. My center finger is giving the direction of current, which is from C to D. Please notice the direction of my thumb. The thumb is pointing towards you in the outward direction, which means that this coil is going to move, the side CD is going to move in the outward direction like this. So, on applying the Fleming's left hand rule on the arm AB, I find out that AB will move inwards and CD will move outwards. That means in totality a force acts on the coil such that this coil moves in the clockwise direction till it becomes vertical. The coil has already gained momentum and now the sides are switched like this. Observe that AB has come on CD's side and CD has come on AB's side. So, now the coil is A, B, C and D. I just have to apply the Fleming's left hand rule once again to observe that now in the second half of the cycle, AB is going to move outwards and CD is going to move inwards like this. Now, this gives rise to a continuous rotation of the coil and to the axle. Now we know the principle behind working of a fan, a mixer, washing machine, etc. It is the force which acts on the current carrying coil which is placed in an external magnetic field. But how can you increase the efficiency of the electric motor? Does using the soft iron core and increasing the number of turns in the coil increase the efficiency of the motor? Do try to find out this answer. Until next time, keep practicing and keep questioning. Namaste.